Sehr geehrte Damen und Herren, mein Name ist Christian Köberl im Namen der Österreichischen Akademie der Wissenschaften, vor allem für die Kommission für Geowissenschaften, deren Vorsitzender ich bin, und die Kommission für Astronomie, deren Vizevorsitzender ich bin, der Akademie der Wissenschaften, begrüße ich Sie ganz herzlich hier in dem Sitzungssaal der Akademie. Let me switch to English since our speaker I don't think understands that much German, and the rest of the talk will be in English anyway, therefore I might as well start in English. So again, a hearty welcome from the Austrian Academy of Sciences. You are here in the meeting room, in one of the meeting rooms of the Academy. Normally, the section meetings are held in this room, and of course a number of other events. Now, as you can feel, the Academy has invested in some renovations recently that included upgrading the air conditioning system, which helps quite a lot. Otherwise, I would have had to refer to our lecturer because he's not only an expert in exoplanets, but also has worked extensively on a phase called Snowball Earth, which is when the Earth was glaciated almost globally, and that knowledge would probably come in very handy right now. Now, let me just very briefly introduce the speaker here. Dorian Abbot is currently in Vienna as a visiting researcher at the University of Vienna, at a department which is kind of next to the one where I'm at. He is funded by the strategic partnership from between the University of Vienna and the University of Chicago, which is where he is from. More details about the CV and past accomplishments of our lecturer will be made by the next speaker, who is the actual host of Dorian at the University of Vienna. This is Eiko Voigt at the Department of Meteorology and Geophysics. So that gives you an idea what meteorologists are up to lately, namely exoplanets, right? Because we learn from the hot air that is produced by certain groups on our planet, how that works on other planets as well. The talk will be approximately 45 minutes, and after that we'll have a chance for questions. I'll be moderating the question period, and after that we have some light summer refreshments, some drinks for you downstairs to freshen up. So once again, welcome to all of you. Thank you for coming in this hot weather, cooling off here a little bit. And thank you very much to Dorian for agreeing to give this public lecture here. So now I'd like to invite my colleague Eiko to give some introductory remarks. Thanks.
Yeah, thanks, Christian. Thanks for everybody for coming. So my name is Eiko Voigt. I'm a professor for climate science at the Department of Meteorology and Geophysics at the University of Vienna. And we had the honor to host Dorian for the last 5 weeks. So he's here for another week in Vienna before going back to Chicago. So just give you a little bit of the details of his life. So he grew up it's Maine, is that correct? Yeah, so he's from Maine. Then did his bachelor studies in physics and mathematics at Harvard University, which he finished in 2004, and then continued at Harvard for a PhD in climate science together with Ellie Zipperman, where he worked on a problem of past climate called equable climates. So here the question was, we know that Earth's climate was very warm 50 million years ago. We call it the PETM. And it's easy to warm these kind of climates if you put enough CO2, but one thing you also need to do is you have to flatten the equator to pole temperature gradient. And this is what Dorian worked on in his PhD, and he suggested a cloud feedback, how clouds might help create such flattened temperature gradient. Then it's 2009, I believe, when he finished his PhD. This is when we met. So Dorian then switched from warm climates to snowball climates. He moved to the University of Chicago to work with Ray Pierre Humbert, also a prominent figure in exoplanet science, Well, to work on Snowball Earth, and the fun story goes, and I tell that every time. So I was a graduate student at Max Planck Institute for Meteorology in Hamburg, and I got an email from Dorian because he just started working on Snowball, and I did my PhD on Snowball Earth. My office mate did his PhD on these equable climates, so 50 million years ago. And Dorian had sent an email to my office mate a couple of weeks earlier asking if they could get in contact. So it turned out that he contacted me and my office mate simultaneously, and he pretended that he didn't know we shared an office, which I have a hard time believing, but this is what he says. And so we had him come over to Hamburg for a visit, and since then we have worked together very productively. So he became an assistant professor in Chicago in 2011 and actually was promoted to associate professor in 2015, still in Chicago. He's been there ever since. And he has a broad range of interests, so including Snowball Earth. He also has a paper which is about what he calls a Steppenwolf planet, so a planet which was ejected away from its star, traveling lonely through space, only being heated by geothermal heat flux. I've also realized now that there was a sci-fi romance story written about that Steppenwolf planet. It's kind of, you can get it freely from the Nature websites. It's just this long. It might be a fun read. He has this tendency to invent interesting names for the mechanisms that he discovers. So Steppenwolf. The other one is Jormungandr. I don't know who knows the name Jormungandr, this snake from the Nordic myth. This is the topic that we worked about on the question of, do you really need a hard Snowball Earth to explain Neoproterozoic geology, or can you sustain climates with an open strip of water close to the equator? He's also, as I said, many other interests, including hurricanes and extreme events. Lately, he's been working on instabilities of Mercury's orbit, and of course, he's been working a lot on exoplanets. So I'm looking forward to seeing the talk today, and it's good to have you. Thanks for coming, and please, your stage.
Thanks for the introduction. Thanks for having me here. So this should be an accessible talk, and if you have any questions about anything, please just raise your hand and I can stop and go through it. So the main objective of this talk is that everyone here, when you leave, should be able to explain what's going on in this diagram. It probably looks complicated now, but that's the goal. And so what we're going to be talking about is this concept of the habitable zone. And it's sort of like the hunting zone of where you would hunt for planets that might have life on them, planets that could be Earth-like. And what we're looking at here on the horizontal axis is the stellar flux. So as you move towards the left, I'll test this guy out. As you move towards the left here, that's getting hotter. And then as you move towards the right, that's getting colder. And on the vertical axis is different kinds of stars. And one important thing we're going to talk about is why the type of star can have an effect on the width of this habitable zone. And then there's different limits here calculated by different people. And the only thing I'm going to point out now is that some of these limits are labeled 1D and some are labeled 3D. And you can see the 1D ones are very different from the 3D ones. And that's going to basically be the main point of this talk. So the contribution that I made with my colleagues was to take it from one-dimensional to three-dimensional, take this calculation. And Aiko, did you forget to mention the funding? I can't remember. Oh, he took care of it, okay. So I'm here on because UChicago and University of Vienna have a strategic partnership. And actually, Jun Yang, who I did most of this work with, is at Peking University, or Beida. And University of Vienna also has a strategic partnership with them and University of Chicago. And so part of what Aiko and I are working on this month is getting a proposal together with Jun Yang, sort of a three-way proposal with all of these partnerships. And most of this work came from when he was a postdoc with me about 10 years ago. And so first I'm going to go through a little bit of background on exoplanets. So exoplanets means an extrasolar planet, a planet that's orbiting a different star. And we've now discovered a huge number of them. So we have 8 planets in our solar system, and then we have a very large number of planets that are orbiting other solar systems. They're mainly detected with 2 techniques that I'm going to go through and show you how they work. The first is called radial velocity, and the second is called transits. And you can see on this diagram that those dominate the detections. You can see that there's a few years where there was just an enormous number of transits, and those are all coming from the Kepler mission, NASA's Kepler mission, which was specifically designed to detect exoplanets in transit. And there were a few major data dumps from that mission, and that's where those go into those bins. And so there's, at this point, maybe like 4,000 total extrasolar planets have been discovered. Okay, so first let's talk about the radial velocity method. So this is going to be a video, and what you're going to see is a planet moving around a star. So the star is here, and the planet's here. Now for both the radial velocity and for the transit method, you can't actually resolve the planet. All you see is the star, and then you see changes in the light emitted by the star, and you infer that a planet is there. So it's not like you get a picture of the planet. And the way the radial velocity works is as the planet orbits the star, it gravitationally tugs it. So from our perspective on Earth, it's going a little bit towards us and a little bit away from us as the planet orbits the star. And that causes a Doppler shift in the light emitted by the star, a slight shift in the frequency of the light emitted by the star, so that the absorption lines of the stellar atmosphere move back and forth. And from that, you can infer the velocity. And if you know the mass of the star, you can then infer the mass of the planet. And so you can see how that works here. So the important thing to know is that the radial velocity method tells you about the mass of the planet. And then the other thing to remember is that in this schematic diagram, you can see the planet and star separately. But when you actually look with the telescope, you just see the star. The planet is not visible. And then the other main method that's used is called the transit method. And so what you're going to see here is, here's the star, and here's the planet. And you're going to see as the planet orbits around the star like this, you're going to see over here that this is the amount of emission that you detect from the star as a function of time. And whenever the planet passes in front of the star, it blocks out a proportion that is proportional to the ratio between the area of the planet and the area of the star. So you can get the cross-sectional area of the planet based on how much the light you detect decreases, and from that you can reconstruct the radius. And so let's look at that one. So this one is the transit method. And what's interesting about this is the radial velocity gave you the mass of the planet, and the transit method gives you the density, so you can put them together. The transit method gives you the radius, so you can put them together and get the density, and then you can start to infer what type of planet it is. So a gas giant planet is going to be much less dense than an Earth-like planet. And so you can use this as a first sort of hint at the geophysics going on. Okay, actually, I'm going to see, does anyone have any questions so far? Yeah?
Why are you showing the discovery statistics of the not fully characterized? And you never get a mass.
What's that?
Why are you showing these discovery statistics?
Can I just interrupt here? We should not have questions during the talk.
Okay.
Because it's recorded and we'll have a microphone afterwards.
Okay, sounds good. Okay, so
Let's keep them for afterwards.
okay, we'll just keep going, and then hopefully I won't lose anybody too much. Okay, so we talked about what exoplanets are. And the first phase that started in about the 1990s, I'll just go back so you can see that again, mid-1990s, was just see how many exoplanets we could detect. And it was actually a surprise that you could detect these exoplanets, because it turns out that there were a lot of planets the size of Jupiter in orbits that are far inside Mercury's orbit, which was a surprise. People didn't expect that. And that caused them to have a huge gravitational effect on their star. So the radial velocity method could detect them easier than people thought. So it was a surprise when they were detected. And actually, the people who did the first detections got the Nobel Prize a couple years ago for that. So the first phase was just racking up as many exoplanets as possible. But the next phase, which is ongoing now, is to try to see if we can find something that looks like Earth 2.0. So something like Earth, as like Earth as possible. And so we want something that's Earth 2.0 orbiting the Sun 2.0. And the Sun is a very specific type of star. It's a G star. It has one solar mass. It's a middle-aged star, so it's about 5 billion years out of its 10 billion year lifetime. And then the metallicity for astronomers means the fraction of all non-hydrogen and helium elements is called the metallicity. And then it's got a similar temperature and a luminosity, the amount of sunlight it emits. And for Earth 2.0, we want something with Earth's mass and radius with a similar orbit so that it has a similar amount of insolation or sunlight that it receives. We should be able to detect signs of water and clouds, maybe continents and plate tectonics, and maybe even life, or what's called biosignatures, signs of life, signatures of life. So that's the dream that we would really like to have. But it turns out that that's a really specific combination, and because of technological limitations, it's hard to do right now. So NASA is planning instruments that might be able to do that in the 40s, but we want to try to get some sort of answer quicker. And so we want to see which requirements we can relax a little bit and still have something Earth-like. And so what you can see here is this habitable zone concept. And what's on the horizontal axis down here is the distance between the star and the planet. And on the vertical axis is the solar mass. And so the sun's up here, and then these light mass stars that we're going to talk a lot about today, called M stars, are down here. And you can see that the habitable zone, as you get to a less massive planet, it moves in closer and closer to the star, and that's going to be an important effect. And the reason is that small stars emit a lot less light, way less light. And so to keep a planet having the same sort of energy that it receives from the star, you have to stick it closer. So it's kind of like if you have the sun is a big fire, so you can stand far away from it in winter and stay warm. But if you have just a little campfire, you're going to have to stand right next to it. And it's basically that effect. And so the habitable zone is a way that we can relax this requirement of Sun 2.0. So we can look for something Earth 2.0, but orbiting a different type of star that has certain advantages that we're going to talk about. And the thing that sort of makes this habitable zone work is something that we call the silicate weathering feedback. And this is an interesting little example because it comes out of the geological literature. And so where this comes from in the geological literature is the faint young sun problem. And so it turns out that the sun and all mean sequence stars increase the amount of light they emit as a function of time, as they change from burning hydrogen only to a combination of hydrogen and helium. And so the sun emitted about 70% of the light that it currently does 4 billion years ago. Yet the geological evidence suggests that the planet wasn't completely ice covered all the time. And so this is sort of a mystery called the faint young sun problem. And the answer that people came up with it is that there's an adjustment in the amount of CO2. And the way this works is that we have a CO2 cycle in the atmosphere, in the Earth atmosphere system, where we have CO2 coming out of volcanoes, and then it's in the atmosphere. It dissolves in rainwater and falls and hits rocks. And then it leaches calcium and magnesium off the rocks, which form carbonates and fall into the ocean crust and then get subducted back into the mantle. And now you can't see that guy. But then eventually that comes out into the atmosphere again. And the critical point is that this step, there it is. This step, the weathering step, depends on temperature and amount of precipitation. And so if you have a warmer, wetter climate, that goes faster and it scrubs carbon dioxide out of the atmosphere. And so that causes the planet to cool. But if you have a planet that wants to be colder because you decrease the amount of sunlight, then this process, the weathering process, goes slower. And so CO2 gets higher in the atmosphere. And this is sort of the dominant explanation for the faint young sun problem, but it also works for the habitable zone. And so we're actually near the inner edge of the habitable zone. But the idea is exoplanets found further away over here, they would have a much higher carbon dioxide level because of the silicate weathering feedback, and they would be able to maintain habitable conditions. So it's an interesting example where you have feedback between different fields, geology and astrophysics. Okay, so I'm going to tell you for a moment about the inner edge and the outer edge of the habitable zone. So I told you what maintains habitable conditions in the middle of the habitable zone, and now I'm going to tell you how you get too hot or how you get too cold. First, how you get too hot. And so what happens is there's sort of two processes that you can, at the inner edge, that can be relevant in different situations. The first process is what I'm showing here is the altitude and the mixing, or the fraction of water vapor. And you can see that as your surface temperature, labeled TS here, gets really hot, you start to get a really high fraction of water vapor high in the atmosphere. And what happens after that is that the water vapor gets photolyzed, it gets broken apart by sunlight in certain wavelengths, and then the hydrogen is lost to space. And so once you get really high fractions of water vapor, you can fairly quickly on geological timescales lose all the water in your whole planet, and you're just dry. And so you're no longer habitable because our definition is liquid water at the surface of the planet. That's process one. Process two, which is called the runaway greenhouse, is actually even more weird and interesting. And so what happens is this is the amount of energy that the planet's capable of emitting to space as a function of the temperature. And it turns out in an atmosphere with a lot of water vapor, the amount of energy the planet can emit saturates. It reaches some limit as a function of temperature. And if you absorb more energy than the planet can emit, you have this runaway process where you go to a totally different climate that's, thousands of Kelvin. And so if that were to occur, Earth would turn into a planet more like Venus very quickly. So those are the inner edge. This is what would happen if Earth crossed the inner edge of the habitable zone. And at the outer edge, what happens is as you add carbon dioxide to the atmosphere, you increase the greenhouse effect, but you also increase the planetary albedo, or the amount of the fraction of sunlight that's reflected. And that's what this curve shows. And so what ends up happening is if you add enough carbon dioxide, the cooling by reflecting sunlight becomes stronger than the warming from the greenhouse effect. And so adding carbon dioxide no longer warms the planet. And so that marks the outer edge of the habitable zone, where the silicate weathering feedback can no longer be effective. Okay, so here's an important point for this lecture. Until about 2013, most of the habitable zone calculations were in one-dimensional and neglected clouds, and that's an important point. And so you can see on the left is, these are papers by the same group. On the left is the 1993 paper, and on the right is the 2013 paper. And in 20 years, they changed the color of the plot from black to blue. So I'm sort of exaggerating. They tuned up the code and, tried to put in new spectral lines and stuff, but it basically doesn't change the main story in those 20 years. And what happened was I read a book about exoplanets, and I noticed that everyone was doing these calculations in 1D, and I said, in climate, we can do things in 3 dimensions, and we get, more accurate results. And so that's basically what we did, what Jun Yang and I did. And so now I want to tell you about M-star planets, which is an important part of this story. Planets orbiting M-stars. So the first thing to understand is that there's a lot more M-stars out there than K-stars and G-stars. So the sun is actually, in terms of main sequence stars, it's a relatively large star. So the sun is a G-star, and I've drawn these pictures of stars in the correct proportions of M-stars to K-stars to G-stars, and also in the correct size in terms of their radius. And so what you can see is there's almost 10 times as many M-stars as G-stars. So that means we're much more likely, the closest extrasolar planet is actually around an M-star. And we're more likely to find an Earth-like planet close to us orbiting an M-star. But there's other advantages too. So the first thing is the transit method detects the fractional change in starlight. And so if the star is smaller, then you get a larger fractional change and it's easier to detect it. The radial velocity method detects the velocity change of the star. And so if it's getting tugged around more, then because it's less massive, then it's easier to detect. Additionally, planets orbiting M stars that are like Earth are going to be packed closer to the star, which makes it more likely that they have a transit and they have a larger radial velocity signal. So there's a lot of observational advantages that make it so the astronomers have identified planets orbiting M stars as major targets for looking for a planet like Earth. But these planets, since they're so much fainter than the sun, the planets are going to have to be a lot closer. And so what this diagram shows is the inner solar system, our system, the solar system, and you can see the orbit of Earth, Venus, and Mercury. And then way inside here is the orbit of a famous M-star system called TRAPPIST-1, which is going to be measured soon with a new telescope that NASA has called the James Webb Space Telescope. And then here, for comparison, you can see the Jupiter moon system. And so the size is actually closer of this stellar system. The size of it is closer to a giant planet moon system than it is to the solar system. And one important thing that you should know is that when you have a planet orbiting a star or a moon orbiting a planet that's very close, you have strong tidal interactions, and you're likely to get caught into a tidally locked situation where you do one rotation of the planet per orbit. And what that means for the planet is that it's always noon on at the same spot, and it's always midnight at the same spot. So we have what we call a substellar spot and an antistellar spot. And so this is a little diagram from the thesis of one of my students that shows what the temperature pattern would look like on a tidally locked planet. And so on the left, we have sort of our normal coordinate system where you have latitude and longitude. And on the right, we've transformed the coordinates. And what we did was we did a three-dimensional simulation with the global climate model to produce this. We've transformed the coordinates so that we have a new system where the substellar point is here and the antistellar point is here. And this angle, which we call the tidally locked longitude, is the angle around, the sort of azimuthal angle, around the substellar to antistellar axis. And you can see that when you do that coordinate transformation, you get a nice symmetry in the system. The other thing to notice about this is that the night side temperature is actually 240 Kelvin, so it's not that cold. So even though there's no sunlight on the night side, it doesn't get that cold because you get a huge amount of atmospheric heat transport. And now I'm going to talk about some of the 3D modeling that we did and the effect that clouds have. So the tool that we're using is called a global climate model. It's a three-dimensional model of the atmospheric motions and potentially the ocean motions. So we have the equations for fluid flow on a rotating planet, thin fluid, so the atmosphere and ocean are relatively thin for an Earth-like planet, and also the radiative equations. And so those are all resolved. And then we have clouds in this model, which have a huge impact on the planet because they can both reflect the sunlight that hits the planet, and they can also absorb the planetary radiation that's trying to get emitted to cool to space, which increases the greenhouse effect. So the clouds can both warm and cool. So if you have a hot day here in Vienna, like today, if the cloud passes over, it feels cooler, and that's the cooling effect. But if you have a cold night here in the wintertime, it's a lot warmer when it's cloudy than it is when it's not cloudy. And so that's the warming effect that clouds can have. So they can do both. And actually, they have a big effect. And so here we took this climate model, we simulated just normal clouds as a function of time. We simulated its temperature with the clouds doing their normal thing. And then we told the clouds to forget to do their cooling job. And the model ran for like a few years, and then it broke and turned into something like Venus. And then we told the clouds to forget to do their warming job, and the entire planet froze over. So just the clouds can take you from a frozen over planet to a planet that looks like Venus. In other words, like the whole range of the habitable zone. So that's how important they are. You've got to get them right. And then it turns out that we're really crappy at modeling clouds. It's the biggest source of uncertainty on climate models. And so this is just a little plot from the modern global warming literature. And what you can see is a bunch of models plotted in gray, wiggly lines. This is the time, and this is the global mean surface temperature. They're all warming because CO2 is being added, but some of them warm more than others. And in particular, the ones that have a strong, what we call cloud feedback, the clouds change to lead to more warming, warm a lot more, and the ones that have a low cloud feedback warm a lot less. And there's a pretty good correlation. And so in other words, the main source of uncertainty in what's going to happen in the future climate is due to our uncertainty in cloud modeling. And the main reason for this is that clouds are what we call sub-grid scale. They're too small to be resolved by our global climate models. So the climate model is stretching around the whole planet so that each grid box is like 100 kilometers by 100 kilometers. But then the clouds have a scale of maybe tens of meters to a kilometer. So they're sub-grid scale. And then there's what we call cloud microphysics, the droplets of water, which determines the cloud reflection and absorption of terrestrial radiation. And that stuff is happening on like a micrometer to millimeter scale. So there's a lot of stuff here that we can't resolve that has a huge effect on climate. And so it's a really important thing that we have to pay attention to. And now back to the tidally locked planets. If we have a very asymmetric situation where we have strong heating on the day side and strong cooling on the night side, we expect to get an atmospheric circulation where there's convection and lifting at the day side, backflow at high altitudes, and then descent on the night side. And when you have a situation like that with a lot of warm, hot air being lifted up by convection on the day side, you expect to get a lot of clouds because the moist, warm air gets exposed to cold conditions. And so you condense out water vapor and form clouds. And when we ran the climate model, that's what we found. And so on the left, we've got the tidally locked planet. And this is a schematic I drew where the low-level winds are all pointed at the substellar point, and a rapidly rotating planet that we simulated kind of like Earth, where the low-level winds are all pointed towards the equator. And wherever the low-level winds are pointed, you end up getting convection and thick clouds. And so the red is a lot of clouds. In the tidally locked case, you get them at the substellar point, and you get them at the equator for the Earth-like case. And so for Earth, we would call this the intertropical convergence zone. And that's why right in the deep tropics, you get this region where there's a lot of clouds and precipitation because the low-level winds are converging there. But this has a big effect on the reflectivity of the planet. This huge deck of reflective clouds right at the substellar point. And so what I'm showing here is the surface temperature of the planet on the left as a function of the stellar flux, where for Earth, it's 1,361. So in the 1D calculations, they said if you pass this threshold, then you you have a runaway greenhouse and you turn into a planet like Venus. But for our 3D calculations, in the rapidly rotating situation, we were able to get them to converge at much higher stellar flux, even at a relatively low surface temperature. And for the tidally locked case, we were able to go even way higher, almost double the stellar flux. So because of these clouds at the substellar point, you can stick the planet to almost twice the stellar flux and stay habitable. And this is important because if we're going to be looking for these planets and trying to observe them and follow up and see what's in their atmosphere, it means that there's a lot more planets out there that we can look at. And the main reason this happens is that the albedo, which is the reflectivity of the planet, is much higher in the tidally locked case than in the non-tidally locked case. And that's ultimately due to these thick clouds at the substellar point. Okay, so now we can try to explain this figure. So what's going on here is, I'll just go over again what these axes are. This is the stellar flux. Value of 1 means that you're where Earth is, you have the same amount as Earth, and this is more and more radiation from the star, and this direction is less and less. This is the outer edge of the habitable zone, according to one-dimensional calculations, and this is the inner edge. We only tried to calculate the inner edge of the habitable zone. We didn't touch the outer edge in this work. If we considered rapidly rotating planets in 3 dimensions, we already significantly moved in the inner edge of the habitable zone. I mean, one thing you can notice about this is if the 1D is correct, that's Earth. It's very close to the inner edge, so like we're really barely habitable. And so it's a little nicer that we have a little more space here. And then this one is the slowly rotating or tidally locked case. And you can see there's just a vast increase in the amount of real estate, potential planets that could be there. We made this plot 8 years ago, so this is listing a bunch of the planets that were detected now, and now there's a whole lot more that were detected there, and now there's a whole lot more. And then this is the tidal locking radius. And so planets that are down here are likely to be tidally locked. And so these planets in particular are likely to have this extra width of the habitable zone. And so that was sort of the main thing that we delivered in this work. A bunch of people have checked that since, and these are calculations with a bunch of different global climate models, and it's showing the amount of cloud at the substellar point. And you can see that all of them produce these clouds at the substellar point. There's a difference in sort of the amount, but the qualitative signal is there in all of them. And this is another example where someone made this same calculation of the inner edge. And you can see that they take into account a few extra things, and it's sort of, this was ours. It causes, some change in the slope and things like that. But the basic picture remains the same with every global climate model that someone's tried to do this for. Okay, so this is science, so we're not supposed to just, even though it's fun to just do theory and calculations with supercomputers, eventually we're supposed to make a prediction that someone can try to test. So I'm going to tell you the prediction that we made, which potentially could be tested soon. Okay, and so to understand that, you first have to know that the temperature decreases with height as you go up in the atmosphere. So even though Icarus fell from the sky because it got too close to the sun, in Earth's atmosphere it actually gets colder as you go up. Okay, so we got that. And then the second thing to know is the infrared emission of an object is larger the higher the temperature of the object. And so if you have a high cloud that's at a low temperature, it emits much less radiation to space. And if you have a low cloud that's at a high temperature near the surface, it's going to emit a lot more radiation to space. And so you can see that on Earth. I'm sorry, this is kind of a complicated plot, but what you're looking at is the longitude and the latitude, and we're looking at the Pacific region. And what's important over here is this is called OLR. It's the infrared emission to space. And then down here, we're looking at the SST, sea surface temperature. So this region is really hot. That's what you should know. So you might expect that the emission to space would be high. But in fact, that's the lowest emission to space. Because over the hot region, you form a lot of these very high convective clouds. And so when you look from space with a satellite, you see those high clouds instead of seeing the hot surface. And the clouds block all of the infrared emission from below and then only emit up this low value. And so that's the effect that we want to look for to find a signal of this. And so back to tidally locked planets, this is a tidally locked planet at a relatively low solar forcing and at a relatively high. And you can see that as we increase the amount of sunlight coming from the star, you get a reversal so that the planetary emission is hot on the night side, and on the substellar point, which is marked by this black dot, the planetary emission is actually very low. So it's like 150 on the day side, and it's like 300 on the night side. And so that would be a very odd signal. You'd be looking at the planet and it would look cold where you expected it to look hot. And that was our proposal of an observational test for this idea. And so you would look at a phase curve. I'm going to show the same video, but in this time we're going to think about it as the emission of the planet. And so you would look at something like this, and you can see that on top of the effect of the planet blocking the star, there's this smaller signal that comes that's higher when you're looking at the day side of the planet and lower than when you're looking at the night side of the planet. And that's called, that's sort of the phase curve amplitude. And so we would look at that. We would look at the planetary emission as a function of time using the James Webb Space Telescope. If we find the right planet, we can do this. And then this is a little prediction we did of time down here and the flux you would measure from the planet compared to an anticipated error bar for this instrument, the James Webb Space Telescope. And what you would do is you would look, when you were looking at the day side, you would peak for a day or two. And you were looking at the night side, you would peak for a day or two. And if the day side is a lot cooler than the night side, that would be a sign that these high convective clouds exist on the day side. So that's our observational test. And then, of course, you could feed this back. So the different climate models give slightly different predictions of the cloud behavior. And so you could model the planet with these different climate models and see which one is better. And maybe that would give you a hint about which one is doing better in its global warming forecast. So you have the different fields talking to each other. Okay, and then I want to show you sort of the update from a cloud modeling perspective. So this is a model that actually resolves the clouds. So instead of having 100-kilometer grid boxes, it's got like, a few kilometer grid boxes. You can only run it for a couple months rather than for many years, and you have to use a lot of computers strung together to do this. And these are calculations by my colleague Jun Yang. This is the substellar point, and the white stuff is clouds, and you can see the animation here. And so when you do this, you get a lot more fine-scale detail. You get interesting, you can see waves in here and different types of clouds, and something that they call cloud streets here, where you get sort of lines of clouds. But you get the same basic picture, that you get these big substellar points. And actually, the grant that Aiko and Jun and I are working on is going to be to use Aiko's fancy, what this is called a cloud resolving model, to do this same problem. And Aiko's model has a few technical reasons that it's actually better than this one. And so we want to check those results again. But the bottom line here is that you get the same sort of basic picture as you got in the global climate model. And then the last thing I just want to say is what I'm working on now, which is trying to deal with the fact that we don't understand the cloud microphysics, the very small scale cloud processes very well. And they're very crudely approximated in a global climate model, and even in a cloud resolving model. And so I'm working on this with Honjo Yang, who's he's not related to Jun Yang, but he was his student at Peking University, and he's doing his PhD with me now. This is a calculation that we did where we took these global climate models. They just have one parameter, a lot of them, that says the size of the cloud particles. And so we just changed it from 7 microns to 14 microns, which is kind of within the uncertainty. And the point of this plot is just that we got a completely different climate. And so it's really important to be able to predict that teeny little parameter. And so this is sort of a schematic of what we want to do. Right now, if you look in a global climate model, the cloud microphysics are what we call monodisperse. There's just one size particle. And that limits our understanding of the fluxes of radiation being reflected and also being emitted to space, which determines the climate. And it also limits our ability to unpack the measurements we make and figure out what's actually happening on that planet. And so that's the before picture and what we want to do. We call this a Jenny Craig picture. Do you guys have Jenny Craig in Austria? No, okay, so this was like a dieting thing, and they would always show the pictures before and after. And so this is my Jenny Craig picture. So after, we want to be able to model in detail the cloud microphysics distribution so that we can calculate these fluxes better and infer what's going on with the with our telescope better. And we're going to use this fancy cloud microphysical model that we call Karma. In the first case, what we've already done so far is sort of use it in one dimension. And so it has all of these fancy cloud processes, things that in the global climate model, we just pick one value for all this stuff. And then we're going to couple it into a global climate model. And we're going to change all of the planetary parameters. So we're going to relax the Earth 2.0 assumption. So before, in this talk, we relaxed the Sun 2.0. We're going to relax the Earth 2.0 assumption and see what effect that has on the cloud microphysics. And the GCM we're going to put this in is called ExoCam. It's a version of the community atmosphere model in the US that's been designed to look at different kinds of planets. And we already talked about how clouds can change the phase curve, which is an important observational signal, but they can also make it harder to measure the spectrum of a planet, which is how you would infer what gases are in it and potentially if it has life. And so we need to be able to model these clouds well in order to pull out information from the spectrum. And so I'm just going to conclude now. So the main point of this talk is that we can use Earth climates models to predict the climate of other planets, such as tidally locked planets. And when we do that, we find that they produce a lot of clouds at the substellar point. That's also consistent with our basic physical understanding. So we can pull from these large numerical simulations, we can pull out a physical understanding that's reasonable, that's not something crazy, and that works across a large number of different models. We can make an astronomical prediction. The prediction is that the clouds at the substellar point should make the thermal emission lower on the day side than the night side. And then the dream is that we could use that, if we potentially find an appropriate planet, we could use an astronomical observation to constrain which climate models can model that better, which might potentially constrain which ones are better at global warming. So, thank you.
Thank you very much, Dorian, for this inspiring and interesting talk. We now have a chance for some questions. And please wait for the microphone and speak into the microphone because the whole talk is being recorded. Thank you. Questions? Okay. Let's start with over there, left. So.
Yeah, what role does the chemistry of the atmospheric clouds are playing? So there are only water vapor clouds. What would change if there are some other?
Yeah, so these models, so we were only modeling clouds, planets that are near the inner edge of the habitable zone, where water vapor is the main potential condensable. If you're looking at planets near the outer edge of the habitable zone, carbon dioxide is an important condensable, and you can have carbon dioxide clouds, and you would need a different climate model. That's actually why we focused on the inner edge. And if you're looking at other types of planets, like hot Jupiters, you can have, all sorts of weird different clouds. And then there's actually planets like Earth that are really close to their star. They can have sand clouds. So rock can be vaporized and then make clouds. But we only considered water clouds.
I'm sorry for this question. You probably hear it a lot of times, but I remember a chapter that I read by Sir Karl Popper on clocks and clouds, titled, and reflecting the problem that there are some systems that are well predictable, the clocks, and some systems are hard to predict, like clouds. And
What was the first one?
Clocks and clouds.
Oh, clocks and clouds. Clocks.
On clocks and clouds. I like the title. Sorry.
Okay.
So of course, all your predictive power and the question whether you can analyze an exo-Earth will depend on the extrapolation of the cloud model.
Yeah.
So my question is, what is your strategy to control the uncertainty, a usual thing in astrophysics, to control the uncertainty while you extrapolate?
Yeah, so...
Then just one hint.
Okay.
I don't know whether this is correct, but somebody told me that at the moment, with the global circulation models, we cannot even model the clouds of the solar system planets.
Yeah, so first the second question, then the first question, and then the second question. So the strategy that I sort of outlined a little bit, the strategy that we use. The first is we try a bunch of different global climate models that were made by different groups with different histories, and we see if they give consistent results. The second is we use more sophisticated models. So these cloud resolving models and what we're trying to develop that will do the cloud microphysics, and we see if they give consistent results. But the ultimate test is observations. And so we made a prediction, and if it turns out that doesn't, it's inconsistent with the observations, then we know that the model's bogus. I mean, that's basically the test. And then for solar system planets, the models do a pretty good job on Earth and Mars. The outer solar system, like the clouds there, I don't know as much about the gas giants and the modeling that people do. And Titan, I don't know actually. I don't know how well they do on those. Those are interesting because they have totally different types of clouds. So they're not water clouds. They're all sorts of other species. So I can't give you a good answer on that.
Do we have other questions?
Question. Dorian, you mentioned at the beginning of your lecture the moist greenhouse effect.
Yeah.
Is this the effect responsible for the loss of water on Mars as well?
Yeah, so it's a similar process, but in that case, it's even simpler. So on Mars, it's just so little mass on the planet that you can just lose all sorts of different species. The moist greenhouse effect, what's interesting is you could lose hydrogen to space, but you can't lose water vapor. It's more massive, so it stays down lower in the atmosphere. And so the moist greenhouse, what happens is you split apart the water so that you've got these hydrogen, and then the hydrogen get lost and the oxygen stays behind. But it's a very similar process.
Let me also ask a question here in between. What is the effect of dust? Because if you have hot planets close to its star, we would expect probably a lot of dust.
So dust has primary effects and secondary effects. The primary effects are the dust can reflect sunlight and absorb terrestrial radiation just like clouds can. It tends to be more of a cooling effect, dust on Earth, so it has a bigger effect on the reflection of sunlight, but that also depends where the dust is. If it's over ocean, then it's more likely to have a cooling effect than if it's over the Saharan desert. The secondary effect is that clouds can actually form around dust particles, and that's a really complicated thing. So there's a whole secondary issue. I think for a warm planet, the complication is a dry planet certainly would be more dusty, but a warm planet might be moister. And the main removal process of dust from the atmosphere is by globbing onto rain particles and getting taken out. And so I'm not 100% sure which direction it would go. Some of these climate models do have dust modules, but as we heard about Karl Popper, those things are obviously, they're even worse. I don't know where there's clocks in clouds and then there's like dust modules in climate models, which is even worse.
We have a question here.
I was wondering if you could show the simulation of the cloud resolving model again. A, because it looks nice, but also because I was hoping you could say something about why it's non-symmetric and how that comes up.
Yeah. So, thank you. Where was that? So the planet's tidally locked, which means it's doing one rotation per orbit. So there is a Coriolis force. There is a difference between east and west because it is rotating. It's rotating a lot more slowly. This planet, I think, has a rotation period of 10 to 15 days. So it's like 10 to 15 times less rotation than Earth. But that small amount of rotation is actually enough to lead to this asymmetry. Now on these planets called hot Jupiters, the rotation is big. It's a Jupiter-sized planet. It's orbiting the star once per day. And you end up getting winds at the substellar point that are like a kilometer per second, I think, really fast. And they advect the hot spot of the planet like 20 or 30 degrees over. And then you can see that in the observations.
You were talking about that you want to validate your measurement, your calculations at some of the planets that are most probably observable with the James Webb Space Telescope. So do you already have a clue what planets you're going to target on? Or
Yeah.
maybe do you even have applied for observation time with the Space Webb?
Okay, so a couple things to say. First is I won't be doing the targeting because I do weird calculations on supercomputers, but I don't actually make astronomical observations. Second is June actually picked one of the two main targets. And so this K272e, I can sort of break down what that means for everyone. So K means Kepler mission. 2, it had 2 phases, one where the thing was working properly and one where it was half broken, but they still were able to get data. So this is the second phase, K2. This is the 72nd planet or star system with a planet. And then the E, the letters indicate the number of discoveries of planets in that system. So it would have been B, C, D, E. This would be the 4th discovered in that system. And that one is potentially habitable. So that's one of them. And then the other one was TRAPPIST. I mentioned a TRAPPIST-1 system somewhere towards the beginning. A couple of those, see if I can find it. A couple of those TRAPPIST planets could be in the habitable zone. And so they're going to be main targets. Let me find that, and there's one more thing I wanted to say. Yes, that was it. So that was a really tiny star with the planets packed in, and I think there's actually 7 planets in that system, and 2 of them could be in the habitable zone. So those will be targets. And the last thing I wanted to say was we don't actually know that Earth-like planets orbiting M stars are going to have atmospheres at all. So the first thing they're going to check with James Webb Space Telescope is they're just going to see if these planets have atmospheres. And if it seems that a few of them do, then there'll be intensive follow-up on some of these candidates. And they'll be looking for at a lot of different things. One thing we'll be looking at the day-side, night-side temperature, but also they'll be looking at the spectral features to see if there's the sort of gases that you might want for an Earth-like planet. Like, you know, it'd be nice to have some nitrogen, some CO2, some oxygen, things like that. Water vapor.
Let me ask a question in between real quick again. If I remember correctly, you mentioned that we can spectroscopically look for the composition of the atmospheres. If I remember correctly, when Kuiper discovered the atmosphere of Titan 70 years or so ago, the only thing that was detected early on was methane. And the main component, which is nitrogen, was only found a lot later. What kind of does that tell us about what to expect for for exoplanets.
Well, so the first point is that tells you that this is an interesting problem. Because, so basically, if, you know, the first person gets the order of magnitude, the second person gets a factor of 2, and then after that, we leave it to the engineers. And these are really order of magnitude problems. You know, you could be missing the main gas, especially something like, I mean, nitrogen, we're gonna have a terrible time inferring. The best you could do is you could look at the Rayleigh scattering and try to infer the pressure, and then you could say, well, there's a lot of other gas that we're not detecting. But I like your analogy to the solar system. So if you look at the papers from the 1970s on like what was in even Jupiter's atmosphere, you get about the same precision that we now get for hot Jupiters. So it's actually, in 50 years, we've gone from what we knew about the planets in the solar system is now what we can infer about these planets that are immensely far away, almost impossible to imagine how far away they are. So it's a good intuition. I think there's a question here.
Sort of a question. We need, life forms need an atmosphere if they're water-based. But let's say you had the reduction of sulfide, that kind of life form, would it need an atmosphere?
Yeah, so all of this whole discussion has been built around this concept of the habitable zone. And the habitable zone is assuming you have liquid water at the surface of a planet that intersects with the atmosphere. And the reason we do that is because on Earth-like life requires liquid water at some point in its life cycle. And then we need it to be interacting with the atmosphere because the only way we could end up detecting this is if it has an effect on the atmosphere. So we're constrained by our understanding of life and by the things that we could detect, what we can look for. But of course, it's possible that there's a whole plethora of other types of life out there that are living under icy oceans or that are working in a completely different way. The problem is if it's under an icy ocean or under the surface of the planet, we can't detect it. And if it's working a totally different way, how would we even know if we found it, right? And so that's why we start the search by looking for Earth-like life. But hopefully, if we detect that, then we expand the search to other types.
Right. Thank you.
More questions? Okay, please.
First of all, thank you for the very interesting talk. And as you said at the very beginning, the main goal is to find the Earth 2.0 around the Sun 2.0. And what's your guess? Will we find it with James Webb in the recent future?
No, because we won't even be looking at Sun 2.0. So they do this sort of every 10 years, NASA does this thing where they sort of say, oh, this is our plan for the future. They call it the decadal survey. And they just did one recently. And they chose to build an instrument that targets like 2040 when it would launch. But of course, James Webb was like 15 years launched after it was supposed to be, so who knows. And that instrument would actually be able to take pictures of a planet like the Earth orbiting the sun. And the way it would work is you would like block out the star like that. And then if you block out the star's light, you can see the planet around it. And so that's the kind of time scale we're talking about. Maybe the 40s, we could look for a planet like Earth orbiting the sun. If we don't, so if it turns out that M-star planets don't have atmospheres and they're not habitable, then everyone will be all excited about that and waiting for the next 25, 30 years.
Yeah, I have to make another excuse because I'm trying to answer this question, if that's okay for you.
Yeah.
But I can ask you a question concerning to your planet statistics afterwards.
Yeah, go for it.
I think for the Earth 2.0, if you accept the term, which means a one Earth mass planet with one Earth radius in an orbit with a 1 year period.
Yeah.
The best chance is to wait for the launch of the ESA Plato mission, which is exactly designed to find such a planet. And if it exists, I think we will find it.
Yeah.
If it's abundant, we'll find it. And I think I don't know whether you agree, but for the analysis for the Earth 2.0, probably we need a dedicated instrument.
Yeah, so Kepler was supposed to be able to find Earth 2.0, but they didn't get long enough time series. And I agree that Plato is going to be much better for that. But even that, we'll just get statistics. So right now, when they try to estimate statistics of Earth-like planets orbiting G-stars, they have to just extrapolate from smaller stars. And so it's another, okay, yeah, go ahead, yeah. Maybe you disagree.
Can I just I'm a fan of the Kepler PI, Bill Borucki. And so to his legacy, Kepler was built exactly for the purpose to statistically determine what fraction of solar-like stars host an Earth-sized planet. Because Kepler was not designed to determine masses and stellar properties. It only has a statistical message. And it was developed later further. That was the reason for my question about the discovery statistics. Because I think accuracy probably is important for you. And that means you need the log of the surface gravity, or the surface gravity. And for that, you need mass
and radius.
And the radius.
Exactly, yeah.
And that is what Plato will do.
You prefer a transiting planet for that reason. But they thought they were going to get, 3 or 4 years of Kepler data for sun-like stars, and then you would have hopefully been able to see one-year orbits, a few examples, but they just didn't get enough continuous data. They knew they couldn't get the mass, exactly. They knew, yeah, I agree 100% with that. But anyways, even if Plato detects, even if we get the statistics of Earth-like planets, it's still going to take 25 years to be able to measure their atmospheres and see what's actually in there. So that's kind of the timescale we're talking about.
Can I ask another hairy issue question? Now, if you have a habitable planet and you assume that it's water-based, you might have large bodies of water that have feedback effects on clouds, on circulation and other things. So does that enter any of the calculations so far? And what difference does it make?
Yes, so that's the sort of thing that a global climate model is decent at. Large-scale feedbacks, where if you put a continent here and oceans here, how's the circulation going to change? And then the large-scale effects on clouds. And we've tried these calculations I showed with lots of different continental configurations. As long as there's a pretty big ocean somewhere, you get the same basic results.
Add to that, if you have a tidally locked planet, then you might have the water distributed rather unevenly, and therefore also life, or?
Yeah, I mean, it's actually interesting. So there's people who do these tidal calculations, and they say that the continent should end up lining up with a substellar point. So your continent should, apparently, the planet should orient itself so the land is near the substellar point. But yeah, that will influence, I mean, you can't get photosynthesis going on the night side, of course. And then on the day side, life started on the ocean on Earth, so it would be nice if you had some ocean there. So it's sort of like, it might require some delicate tuning, but the hope is in a statistical sense, you would get enough planets that if there really were life on none of the ones we detect, you would start to have a constraint, at least on the frequency of life in the universe.
So, do we have any more questions that need to be asked in the presence of an audience, or can be asked downstairs individually? If not, then thank you very much again for a very inspiring talk. And thank you all for coming, and there are still some drinks downstairs for the next, half hour, 45 minutes or so. Bye-bye.